You know, when most of us picture a robot, we immediately default to, like, the movies.
Oh, for sure.
We picture these shiny metal humanoids with glowing red eyes or maybe clunky talking trash cans rolling around a spaceship.
Right, exactly. The classic Hollywood tropes.
Yeah, but I read a fact today that it absolutely shattered my perspective.
Okay, let's hear it.
So the next time you board a modern passenger airliner, right, you walk down the jet bridge, take your seat, you are essentially stepping inside a giant flying robot.
It's true. It really is.
Like the autopilot system can control that plane entirely through takeoff, normal flight, landing. The two human pilots sitting up in the cockpit, they're mostly just there to manage the machine.
They're monitoring systems.
All right. While the robot actually flies you through the sky. It's wild.
It forces a complete reset of how we define these machines, doesn't it?
It really does.
Because our cultural imagination of robotics is, it's so tied up in that fiction you mentioned that we often miss the reality of what the field actually is today. So our mission in this deep dive is to look past all that. We're looking at a massive stack of interdisciplinary research today. We want to understand what robots actually are, how they're engineered to physically move and feel, and really how they are fundamentally rewriting the future of our workforce.
And our society.
Exactly. We aren't just looking at the what today, but the why. Why are these machines designed the way they are? And, why does this matter to your daily life?
Okay, let's unpack this. Because before a robot can cook your dinner or, I don't know, build your car or explore Mars, we have to understand its basic anatomy.
Right, the physical building blocks.
Yeah, moving from the abstract concept to the actual hardware. And the foundational design of any robot comes down to four main aspects. You've got a power source, mechanical construction, a control system, and software.
Yep.
But the part that absolutely fascinated me in the sources was the mechanical construction, specifically the actuators.
The muscles.
Right. These are basically the robot's muscles. They take stored energy and convert it into actual physical movement.
And the way engineers are building those muscles right now is, it's undergoing a massive evolution.
Yeah.
Yeah. Because for a long time, the industry standard was just standard electric motors.
Like the ones in RC cars or whatever?
Sort of, yeah. You had your basic brushed and brushless DC motors for smaller portable robots, and then these heavy-duty AC motors to drive massive industrial arms on factory floors.
Right.
But engineers are moving far beyond just standard gears and spin-it magnets now. Take piezoelectric motors, for instance.
Piezoelectric?
Yes. So instead of using electromagnetism to create rotation, these motors use tiny piezoceramic elements.
Okay, what does that mean exactly?
Well, when you apply an electric field to these ceramics, they literally change shape. They vibrate thousands of times a second.
Wow. Which means they can achieve incredibly precise movements, right? Like down to the nanometer.
Down to the nanometer.
That is insane.
It is. They offer this incredible combination of resolution, speed, and force for their tiny footprint. But of course, if you need broader, more powerful movements, engineers are looking at pneumatic artificial muscles.
Right. The research called these air muscles, I think?
Yes, air muscles. They're specialized tubes designed to mimic biological muscles. When forced air is pumped inside them, they can expand up to 42%.
That's a huge expansion.
It really is. And beyond that, there are electroactive polymers. These are plastics that can contract substantially when exposed to electricity.
Like, how substantially?
We're talking up to a 380% activation strain.
What? That's crazy.
Yeah, those have actually been utilized to build realistic facial muscles in humanoid robotics, which we'll get to later.
Okay, but the material that really stopped me in my tracks was the elastic carbon nanotubes.
Oh, yes. The strength on those is unbelievable.
I was looking at the physical specs on these things, and it's staggering. It said an 8-millimeter wire of this material, which is only about 3/8 of an inch thick?
Yeah, thinner than your pinky finger.
Right. That tiny wire could feasibly replace a human bicep.
It's incredible.
That kind of physical power packed into something so small, it means future robots won't just match human strength. They're going to easily outperform us by orders of magnitude.
Which introduces a massive engineering problem, actually.
Because they're too strong.
Exactly. Strength is useless and highly dangerous, really, if it isn't controlled. If a robot is incredibly strong and perfectly rigid, it essentially becomes a wrecking ball.
Oh, right.
If it swings an arm to pick up a cup and miscalculates by an inch,
It just shatters the table.
right through the table.
Okay, so that brings up a fascinating concept from the reading called series elastic actuation. or CA.
CA, right.
If I'm understanding the mechanics correctly, it's about introducing intentional softness into the machine.
Yes.
I picture it kind of like the cartilage in human joints or like the shock absorbers on a mountain bike.
That's a great analogy.
You want some elasticity between the rigid motor and the thing it's interacting with so the machine doesn't just destroy whatever it touches.
What's fascinating here is that this intentional elasticity is fundamentally about safety and energy efficiency.
How so?
Well, historically, industrial robots were kept in heavy steel cages on factory floors.
Right, because they were way too dangerous for humans to be near.
Exactly. They were perfectly rigid, so any collision transferred a massive amount of kinetic energy. But by introducing an elastic element between the motor actuator and the load, SEA provides immediate shock absorption.
It literally softens the blow.
Yes, it lowers the reflected inertia. So if a robot with SEA accidentally collides with a human, or just an unexpected object in an unstructured environment,
The elastic element absorbs it before the motor even registers the collision.
exactly. It makes the machine incredibly robust, but physically forgiving.
But here's the catch, right? Having incredibly strong, forgiving muscles is great, but all that power means nothing if the machine is just bolted to the floor.
Right, it has to move.
Before it can interact with our world, it has to be able to navigate it. So how do we get these things to actually move? The engineering contrast between wheels and legs is wild to me.
Oh, it's a huge debate in robotics.
Because wheels are incredibly efficient. Like, there's that robot from Carnegie Mellon University called a ball bot.
The ball bot, yes.
It's about the size and width of a person, and it balances entirely on one single round ball.
Balancing on a single point like that relies on inverted pendulum dynamics.
Which sounds incredibly complicated.
It's actually something you intuitively understand. If you've ever tried to balance a heavy broomstick upright on the palm of your hand,
Oh yeah, you're constantly darting your hand around to keep it from falling.
exactly, the top of the broom wants to fall, so your hand has to constantly dart back and forth underneath its center of gravity just to keep it upright.
So the ball bot is doing that.
Yes, mathematically. It's using internal motors to constantly drive the ball to counterbalance a fall, adjusting hundreds of times a second.
Which is brilliant for flat surfaces.
Right, flat surface.
But we live in a world of stairs, curbs, uneven terrain, which is why walking on two legs by pedal locomotion is the ultimate goal.
It is the holy grail of movement.
But anyone who has seen early attempts at this knows it's an absolute nightmare.
Oh, it's so difficult.
Like, take Honda's famous Asimo robot. It relies on an algorithm called the zero moment point, or ZMP.
ZMP, yes.
The robot's onboard computer constantly runs these complex physics calculations, right? Trying to keep the total inertial forces, like Earth's gravity, plus the acceleration of the robot's own limbs, exactly opposed by the floor pushing back on the foot.
Right, the goal is to leave absolutely no moment or rotational force that would cause the robot to tip over.
The math is flawless, but the physical execution.
It's heavily constrained.
Yeah.
Because the ZMP algorithm requires keeping the foot perfectly flat against the floor to calculate that opposing force, the robot has to keep its knees perpetually bent to absorb any shock.
Right, which is why observers always joke that Asimo looks like it desperately needs to use the bathroom when it walks.
It does. It looks incredibly stiff and unnatural, and it requires perfectly flat floors.
But engineers are moving past that stiffness now, right? Toward dynamic balancing.
Yes, thankfully.
Like, there's a bipedal robot called Dexter, built by AnyBots. Instead of trying to prevent a fall completely, it constantly monitors its momentum and practically throws its feet forward to catch itself.
To the point where it can literally perform jumps.
It can jump. And then you have passive dynamics, where the robot uses the natural momentum of swinging its limbs to power the next step.
Which is much closer to how you and I walk.
Yeah, we don't calculate floor resistance. We just lean forward and catch ourselves.
Exactly. And that approach can actually increase efficiency tenfold over the ZMP algorithm.
Tenfold. That's huge.
And that pursuit of movement efficiency isn't limited to the ground either.
Oh, right, the flying ones.
There is an entire subfield dedicated to biomimetic flying robots. These are machines taking direct inspiration from mammals, birds, and insects.
Because traditional drones are kind of inefficient, right?
Very. Traditional aerial drones use fixed propellers, which are loud and consume massive amounts of energy just to hover, but biomimetic robots use flapping wings to generate lift and thrust.
Like a bird.
Like a bird. Flapping wings drastically increase aerial maneuverability and reduce the energy consumption required to stay aloft.
Okay, I have to push back a little on the whole engineering marvel narrative here, though.
How come?
Well, looking at this research, it feels like human engineers aren't actually building the best machines from scratch. They're basically just cheating off of Mother Nature's test.
That's a funny way to put it.
I mean, they're just copying millions of years of animal evolution. I'm reading about bat-inspired robots with specialized shock absorbers for landing, flying squirrel prototypes, raptors with adjustable feathered wings to prevent aerodynamic stalling.
Even tiny robotic beetles.
Exactly. It's all just copied from nature.
Well, cheating is a harsh word, but you're not wrong. I mean, why reinvent the wheel when evolution has spent 500 million years doing the rigorous R&D for you? Evolution has already solved the most complex fluid dynamics problems on Earth. Consider this. There's a robotic fish that models carangiform swimming.
Carangiform.
Yes. It's the specific undulating way certain fish move the back half of their bodies and tails. Engineers replicated that biological movement, and the robotic fish achieved greater than 90% propulsive efficiency.
90%?
Yes, it accelerates and maneuvers far better than any man-made submarine or boat, and it creates significantly less water disturbance.
That's wild.
In fact, back in 2014, one of these robotic fish actually outperformed some real biological fish in average maximum velocity and endurance.
Wait, it beat the actual fish?
It beat the actual fish.
Okay, so we have carbon nanotube muscles, machines that can balance like a broomstick on a ball, jump on two legs, flap like a bat, and apparently outswim an actual fish.
Yes, quite the resume.
But moving fast is incredibly dangerous if the machine is blind and numb.
Absolutely.
All that beautiful locomotion means nothing if it just crushes everything it touches. So how do we give a machine a sense of touch? We all know about LiDAR, radar, and sonar, right?
Bouncing lasers or sound-off objects to map a room.
Yeah, so the robot doesn't walk into a wall, but the holy grail of robotics right now seems to be tactile sensing.
Giving a machine a true sense of touch is arguably more difficult than teaching it to walk.
Really?
Oh, yes. Current robotic hands receive a fraction of the tactile information your biological hand does, but engineers are closing that gap. Recent breakthroughs have developed a tactile sensor array that physically mimics the mechanical properties and touch receptors of human fingertips.
And the construction of this is amazing. It has a rigid internal core surrounded by a conductive fluid, which is all contained within a flexible elastomeric skin.
Exactly.
Here's where it gets really interesting. The mechanism here is brilliant. When that artificial skin touches an object, the pressure physically deforms the fluid path around the electrodes inside the finger.
Changes the flow.
Right. Think of the conductive fluid as a fast-moving river. When the robot presses its finger against a surface, it's like dropping a boulder into that river. It alters the electrical current's flow.
And by measuring those electrical impedance changes, the computer can instantly map the exact forces and pressure the finger is receiving.
To put it simply, think about trying to pick up a raw egg while wearing a thick, rigid winter glove.
A classic problem.
You have zero tactile feedback, so you either drop the egg because you aren't gripping hard enough, or you just completely crush it.
Right.
High-resolution tactile feedback allows the machine to adjust its grip dynamically in real time.
And the real-world applications of that technology are life-changing.
Oh, for prosthetics, right?
Yes. Back in 2009, scientists in Europe and Israel integrated this kind of tactile feedback into a prosthetic hand. Patients using the prosthesis were able to actually sense objects through the artificial fingertips.
This must have been incredible for them.
It was. Because they had that feedback, they could write with a pen, type on a keyboard, perform fine motor movements that are literally impossible with a numb prosthetic.
And it changes industrial robotics too, right?
Absolutely. It fundamentally changes end effectors, which are the tools at the end of a robotic arm. Instead of friction jaws that use sheer crushing force to hold an object, factories now use soft, compliant suction cups powered by vacuum generators.
Because it won't break things.
Exactly. That natural compliance prevents damage to fragile items during manufacturing or packaging.
Okay, so touching an egg is data collection. But collecting data isn't enough, right? The robot needs software to make sense of that data, and more importantly, to make sense of us.
Yes, the cognitive side.
That leads us directly into human-robot interaction, or HRI. The literature makes it very clear that interacting with humans is technically grueling for a machine.
It really is. Recognizing human speech in real time is a massively difficult computational problem.
Because human speech is chaotic.
Extremely chaotic. When you or I speak, we intuitively understand each other. But for a computer parsing audio waves, the sound of a specific word varies wildly based on your regional accent.
The background acoustics of the room.
Exactly. Your volume, the specific word you spoke immediately prior, and even your biological health.
Like if you have a cold.
Yes, if you have a head cold, your acoustic signature changes. Translating that chaotic acoustic data into reliable, executable code is a monumental hurdle.
And people have been trying to solve this for decades. The history here is wild. There was a guy named Michael J. Freeman who developed a teaching robot all the way back in 1974.
For elementary students in the Bronx, right?
Yeah. He literally had to invent a way to convert digital computer memory into rudimentary verbal speech using pre-recorded computer disks just to get the machine to interact.
We've come a long way from 1974 to modern emotional robotics.
We really have. Now you have Hanson Robotics creating these highly expressive synthetic faces. They use an elastic polymer rubber skin mesh animated by dozens of subsurface motors all embedded over a metal skull.
It's visually stunning.
And then you have machines like Kismet, which engages in social exchanges with a vast range of facial expressions, and Robin the Robot, which uses AI to analyze emotions and comfort children experiencing stress and anxiety in medical clinics.
It's incredible work.
But I have to ask a direct question here.
Go for it.
Why go through the terrifying trouble of putting a rubber face on a robot? Why do we need our machines to have a personality?
Well, if we connect this to the bigger picture, it comes down to human evolutionary psychology and a field called effective computing.
Effective computing.
Right, which is the processing and simulation of human emotions by AI. Human brains are hardwired for pareidolia.
Meaning we look for faces in things.
We look for faces in absolutely everything, and we are biologically programmed to read facial expressions to determine threat levels.
Okay, that makes sense.
So if a machine in a hospital is approaching a child to draw blood, an expressionless metal box triggers a deep evolutionary predator response.
Oh, wow. I never thought of it like that.
Yeah. But a rubber face that smiles hijacks our evolutionary biology, tricking our brains into trusting it. Studies show that for many people, interacting with a socially expressive robot can drastically reduce their negative feelings or anxieties toward machines.
But it can also backfire, right? The uncanny valley effect.
Yes, the uncanny valley.
If the face is slightly off, it bolsters strong negative prejudices. It's just creepy.
Very creepy. But the fundamental reality is that if these machines are going to exist in our domestic environments, our hospitals, our elder care facilities,
the way we command them must be intuitive.
Exactly. People with absolutely no technological skills need to be able to work alongside them comfortably.
And working alongside them is no longer some distant, abstract future. It is happening right now. These socially adept, physically capable machines are rapidly moving out of the laboratory and into the global job market.
They are everywhere.
The applications we are seeing in the sources are wild. You've got Spice Kitchen, which ran fully robotic food bowl restaurants in Massachusetts where machines cooked the meals.
Oh, and AI-assisted precision agriculture, completely automating complex farming tasks.
And you have the reality of lights-out factories.
Yes, lights out.
IBM had a keyboard factory in Texas that was fully automated, meaning they could literally turn off the lights because there were no human eyes that needed to see the assembly line, and that was as far back as 2003.
The efficiency and productivity gains of automation are undeniable, but, they come with a profound macroeconomic cost.
Which we have to talk about.
We do. A 2017 study found that automation alone puts 47% of all U.S. jobs at eventual risk.
47%. That is half the workforce.
And theoretical physicist Stephen Hawking warned in 2016 that the automation of factories has already decimated traditional manufacturing jobs, and the rise of advanced AI is likely to extend this job destruction deep into the middle classes.
Right.
His assessment was that eventually only the most caring, highly creative, or supervisory roles might remain untouched by automation.
At the same time, the transition isn't just about replacement, is it?
Not entirely, no.
Because there is a massive rise in cobots collaborative robots. Humans are still vastly superior at light-duty jobs involving unpredictable creativity, nuanced decision-making, and physical flexibility.
Right, machines struggle with that.
So cobots are designed to work safely in close spaces with humans, taking over the dirty, dangerous, or physically monotonous work.
Which is where that series elastic actuation we talked about comes in handy.
Exactly, because they're safe to be around. Think about your own job for a second. How much of your 9 to 5 is repetitive data entry, sorting, or heavy lifting?
Too much of it, probably.
Imagine a workspace where a cobot does 100% of those mundane tasks, leaving you only with the high-level creative decision-making. And building those machines is an industry in itself. A global data report projects the robotics sector will hit $568 billion by 2030.
That's $500 billion.
So what does this all mean for you? You have to contextualize this shift for your own career trajectory. Are you losing a job to an algorithm, or are you gaining a highly efficient mechanical coworker?
This raises an important question, macroeconomically speaking. The massive displacement of routine workers is leading to serious, high-level proposals around universal basic income to replace lost wages for those who cannot transition into creative or supervisory roles.
Right, which is a highly debated topic.
Extremely debated. Meanwhile, several European countries are officially including robotics integration in their national economic programs, specifically trying to promote healthy, safe cooperation between human operators and cobots.
To boost national productivity without devastating the working class?
Exactly. The transition of the global workforce requires deliberate, thoughtful policy right now, regardless of where you stand politically on solutions like UBI.
And while society scrambles to figure out the economic policies for today, the engineers are already designing the robots of tomorrow.
The frontier.
Let's look at the absolute frontier of this technology. One of the most mind-blowing concepts we uncovered is evolutionary robotics.
Oh, this is fascinating.
Instead of a human software engineer sitting down and meticulously coding every single behavior, researchers are using evolutionary computation. They basically create a simulation, drop a massive population of digital robots into it, and let them compete using a mathematical fitness function.
It is literal digital natural selection.
Literal evolution.
Let's say the goal is to get a simulated bipedal robot to walk across a room.
Yeah.
In generation 1, they all fall over immediately.
Naturally.
The fitness function measures which robot fell the furthest distance from the starting line. The ones that perform the worst are deleted, essentially killed off.
Wow.
The simulation takes the underlying code from the ones that fell a few inches further, combines and mutates their code, and breeds a new generation.
And they just repeat this.
They repeat this process thousands of times. Over many generations in a simulation, a highly capable, completely organic-looking walking behavior emerges, and no human engineer directly coded it.
The machine teaches itself how to exist. And where does that trajectory ultimately take us? Professor Hans Moravec from Carnegie Mellon's Robotics Institute predicted a timeline for robotic intelligence way back in 1997.
Moravec's timeline, right?
He estimated they would reach the mental capacity of a lizard by 2010, a mouse by 2020, then a monkey, and eventually hit human-level cognitive capacity by around 2045.
And that timeline wasn't even factoring in quantum robotics.
What is that?
Quantum robotics is the study of running these complex neural networks and robotic algorithms on quantum computers, giving them processing power that vastly outperforms traditional digital brains.
I don't even know how to process that.
We are looking at an exponential curve in capabilities. We are moving away from rigid machines that simply execute rote, pre-programmed tasks toward highly adaptive systems that learn through simulated evolution, process information on a quantum level, and alter their own behaviors based on environmental feedback.
It really is a staggering journey. I mean, we started today looking at the literal nuts and bolts, piezoelectric artificial muscles vibrating thousands of times a second, and ball bots balancing like a broomstick on a hand.
Yes, mechanical foundations.
We explored how these machines physically feel the world through conductive fluid skin, how they manipulate our trust using emotional synthetic faces, and how they are fundamentally reshaping our entire global economy with the rise of the workplace cobot.
I want to leave you with a final thought that builds on everything we've explored today.
Please do.
If evolutionary robotics allows machines to adapt, iterate, and evolve purely through digital natural selection, completely free of human coding, and quantum robotics grants them a level of processing power that we can barely comprehend.
Yeah.
At what point do we stop thinking of robots as simply programmed tools and start viewing them as an independent synthetic species evolving right alongside us?
Wow, now there is a thought to keep you awake tonight.
True.
The next time you look up and see a passenger airliner cruising at 30,000 feet, remember, you're looking at a giant flying robot, and it is just the beginning. Thank you for joining us on this deep dive. Go look at the machines in your own life through a brand new lens.